Electrostatic or Madelung energy. As we know that ionic crystals are the periodic arrangement positive and negative ions. These crystals are highly ordered lattices. The dominant interaction responsible for the stability of such crystals is the electrostatic Coulomb interaction between ions. Therefore, the total energy of the crystal must be constructed Coulomb's interaction between all pairs of ions, between all pairs of ions. Let us consider two ions I and J. They are separated by a distance Ij. It is ith is ith ion and j ion. The distance between these two is Rij. That is, give I give j. The electrostatic interaction energy between these two ions is given by give Ij give I give j by epsilon naught Rij. The interaction is attractive per opposite charges and repulsive other. mass and repulsive for the same charges. In ionic crystal, both type of interaction are present simultaneously. The stability of a system arises from a delicate balance to construct the total electrostatic energy of the crystal. We must sum over all the interacting pair of ions, that is sum over I not equal to j, mu ij. There is a possibility that each pair is counted twice in the whole system. That is, mu ij and mu ji. To avoid such counting, we introduces a factor half so that u is 1 over 2 summation I, j is not equal to I mu ij. Similarly, we can also write the interaction of single ion I with the rest of the ions present in the crystal. The equation can be written as mu summation over I ui, which further means that this is I not equal to j, ui j. Since we know that every lattice site is equivalent due to the translational symmetry. So the energy ui is the same for all ions of the same nature. Let us consider a reference ion I placed at the origin. Let us we consider the interaction I with all other ions in the crystal. The reference ion has a charge minus E. Then its interaction with another ion at a distance Rj, at a distance of Rj is Uij is equal to minus E is the reference charge and plus minus E are the charges are the charge at a distance J from this reference charge. The sign of depends on whether ion is positive or negative. Writing this equation, for I interacting with all other ions in the crystal. So means summing over all ions, that is ui is equal to I not equal to j uij, where uij is minus e square 4 pi epsilon naught 1 over rj. So our equation will be minus e square 4 pi epsilon naught summation over j plus minus 1 divided by rj. It is ui. The distance rj depends on the lattice structure. We can represent this rj in terms of nearest neighbor distance. As we have discussed in the previous lecture, that rj is equal to pj, or this equation is equal to rij pij into r, as discussed in our previous lectures, where pj as a dimension is quantity, factor is a pure number. This term depends on crystal geometry. So our equation will be ui minus e square 4 pi epsilon naught or summation over j 1 over plus minus pj. Because from this equation rj by r is equal to pj. Here alpha is equal to summation over j plus minus 1 over pj, that is called Madelung constant. Thus the energy of the single ion will be ui is equal to minus e square divided by 4 pi epsilon naught r into alpha. If there are n number of ions, then the total energy will be equal to ui, that is minus n alpha e square divided by 4 pi epsilon naught r. Another important point is that the electrostatic interaction alone will collapse the crystal, since the energy may be more negative as the ion approaches each other. Therefore, we must include a short range repulsive interaction represented by ur is equal to lambda e minus r divided by rho. Or if we have n number of ions, then ur is equal to n lambda E minus R by rho, while this repulsive interaction depends upon the nearest neighbor, which is represented by Z. So nz lambda E minus R divided by rho. Here R is the nearest neighbor and rho depends, shows that half the repulsive interaction decay with the distance, and this lambda shows the strength of this repulsive interaction. So the total energy will be equal to the sum of the repulsive plus the Coulomb interaction energy. It is U total is equal to nz lambda E minus R divided by rho minus n alpha E square divided by 4 pi epsilon naught R. Or U total is nz lambda E minus R by rho minus n alpha E square 4 pi epsilon naught R. The balance between the long range attraction and the short range repulsion is what stabilizes the crystal structure. The equilibrium separation can be obtained by du total divided by dr at r is equal to r naught. It is equal to 0. D divided by dr of the total energy n z lambda E minus R by rho minus n alpha E square 4 pi epsilon naught R. R n z lambda E minus R by rho minus 1 over rho, differentiating the power with respect to R, minus n alpha E square 4 pi epsilon naught R square minus 1 over R square, or minus n z lambda E minus R by rho minus n alpha E square 4 pi epsilon naught R square, and that will become plus. Our equation is minus z lambda E minus R by rho 1 over rho plus n alpha E square divided by 4 pi epsilon naught R square equal to 0. Here we have n. R nz lambda E minus R by rho is equal to n alpha E square rho divided by 4 pi epsilon naught R square. It is z lambda E minus R by rho is equal to n alpha a square rho divided by 4 pi epsilon naught r square. Using the value of this z lambda E minus r by rho in our previous equation of the U total energy, that is UT is here nz n alpha E square rho divided by 4 pi epsilon naught r square minus n alpha E square 4 pi epsilon naught r. Now this is at the condition when r is equal to r naught. So our equation will be n alpha E square rho divided by 4 pi epsilon naught square minus n alpha E square 4 pi epsilon naught r naught. N alpha E square 4 pi epsilon naught r naught. Taking this common, so negative this common, so we will get 1 minus rho divided by r naught. This is UT. So this term is called Madelung energy. That is Madelung energy is 1 over 4 pi epsilon naught r naught and n alpha E square.